Are you excited to have a break? Yes? Can't wait. Okay, good. Now usually what I do is in the last lecture in a review session, I talk in general about the most important things, we learned in class, yada yada. This time we're going to do a little bit different because the calculus coordinator has made available 2 final exams. So I looked at those final exams and I noticed that there's a couple of types of questions that we maybe didn't cover as much in the class as we might have. And since they showed up in the practice finals, there's a chance that they might show up in the final. Frankly, you have no idea what the final looks like. I haven't seen it. But I think that we should go over such problems and also a couple more that I think I could have explained differently and maybe better. So we're going to go over that. If we have time left, you guys are welcome to suggest problems and we can do them. Also remember there's problems at 4 p.m. to 6 p.m. today. So you guys have another chance to ask any questions you want about any problems you want. Okay, so let's start with the basics. The most important things that we learned in this course, what do you think that is? What are the basic concepts here? Limits. What else? Derivatives. Okay, that's great. Derivatives. So first question is, what is a differentiable function? What is a differentiable function? What do you think? Okay. What's a differentiable function?
Function that you could derive.
Okay, a function that has a derivative. Okay, what's that? Okay, the derivative is the slope of the tangent at a particular point, right? In order for the function to be differentiable, to have a derivative, it needs to have a tangent line at every point. So you cannot have corners or jumps. So differentiable function no corners or jumps. For example, this function right here is not differentiable. An example of this function would be what? What do you think would be a function that has a corner and is therefore not differentiable? Absolute value, that's right. So it's good to remember this example, but it's especially important to remember the definition of differentiability. Differentiability means that at every point there's a tangent line associated to the function at that point. And this point has no tangent line associated to it, you see, because there's not really a tangent line. You can draw it anywhere you want. It's not really a tangent line, so it's not differentiable. What about continuity? What does continuity mean intuitively? Come on, we did this before. Peter, you don't need to leave the pen. That's right. So, no need to lift the pen. I hope you guys didn't raise your hand before because it's so obvious, not because you didn't know. This is a very basic question, okay? You need to be aware that, for example, this function is not continuous. And what would be an example in practice of functions that are not continuous? If you were asked to say what a non-continuous function would be. Well, most of the functions we learned, polynomials, exponentials, logarithms, even the absolute value function. Is the absolute value function continuous? It's continuous because you can draw it without lifting the pen, right? So if you want to construct an example of a function that is not continuous, you probably should come up with a piecewise defined function, right? To define a piecewise defined function, you can define one part over here using one formula, the other part using another formula, they don't need to match up. The function does not need to be continuous. So example, piecewise defined functions. Now, there's an implication in here. One of them is more general than the other. What do you think? If a function is differentiable, then it's continuous? Or if it's continuous, then it's differentiable? The first one? Okay, who votes for the first statement? If a function is, hold on, if a function is continuous, then it's differentiable. Okay, who votes for the second statement? If a function is differentiable, then it's continuous. Ah, good. Good, you guys are good. So, does anybody want to explain this to me? You want to try? No? Okay, if a function is differentiable, then it cannot have corners or jumps, so it better be continuous, otherwise you would have a jump, right? So differentiable, in a sense, is a stronger condition. We say in mathematics, it's a stronger assumption than continuity. It's harder for a function not to have any corners or jumps than just to be continuous. Okay, fine. Let me give you an example, a non-trivial example of a question involving continuity. Problem. Suppose that you're given the function, let's see, cosine of x for x less than 0 and x squared plus a for x bigger or equal than 0. And the question is, for what value of a is the function f of x continuous? Okay, so let me first explain the problem a little bit better. This number a here, you may not be familiar with this idea, but this is a function that has a parameter. So a is what we call a parameter. It's another variable there. You know, it's hanging around, but it's a constant. You don't really know what the value of a is, but it's a constant throughout the definition of the function. So for example, if you said a equals 2, then you have a perfectly well-defined piecewise defined function. If you said a equals 5, same thing. So a is just a parameter. You don't know what it is, but it's there. So the question is, for what values of a, of the parameter a, the function f is continuous? Okay? In general, one thing I would recommend to do in almost any problem really is to draw carefully the problem, if you can. For example, in this case, we have the function cosine of x for x less than 0. The function cosine of x looks more or less like this. Okay? The x less than 0 means that I'm going to draw an empty ball in here, indicating that the function is not defined by, at 0, is not defined by this formula. For x bigger or equal than 0, the function is defined by the formula x squared plus a. So it's basically a parabola, and it has a full ball in here. So this is cosine x, and this is x squared plus a. Okay? Now, question again, for what value of a is this function continuous? So we're going to look graphically, you're going to look for shifting this graph up and down by changing the value of a until the two functions match up. Okay? So that's, graphically, that's how you think. You move this function around until the two of them match up. All right? Okay, so what do you think would be a in this case? 1? Great, that's a great intuition. Okay, if the function, if the value of a is 1, then you move this function up and down here until they match up, and they match up at 1, and you're good. Okay, let's do this algebraically, so that you know how to do this systematically, just in case you don't see the answer right away. because the problem might be more complicated, for example. So for continuity, we need the limits. Let's see. Let's calculate the limit when x goes to 0 from the left of f of x. So we want to study the continuity specifically at 0, right? So we want to calculate the limit as x goes to 0 of f of x. But what happens is the function has two different definitions, one from the left, one from the right. So we're going to break this down into the limit from the right of f of x and the limit from the left. The limit from the left of f of x is equal to the limit of the function cosine of x. Okay? Once again, when x is negative, f of x is cosine of x. So I can write the limit when x goes to 0 minus of cosine of x. And that limit is 1. Okay. When x is positive, so when x goes to 0 plus, the function f of x is equal to x squared plus a. And this limit is equal to, okay, when this is a polynomial, so when x becomes really, really tiny, this goes to 0, this is a, so the whole thing goes to a. So now you can see how we need to require that a is equal to 1. Because for continuity, at x equals 0, both limits must be equal. Therefore, a must be equal to 1. All right. So this brings up a couple of things that we did in class. We talked about the limit of a function when x goes to 0. Okay? That's the value of the function as x becomes closer and closer to 0. We talked about the limit from the left, the limit from the right. That's what happens to the function when x is approaching 0 but is negative, or when x approaches 0 but is positive. All these are important concepts that are sure to show up tomorrow for the exam. Okay. All right, let's do another problem. This is a problem that we actually did not do in the class, but it was in the homework. And I'd like to talk about it, is to show that the following equation has exactly one root. And the equation is 4x is equal to cosine, actually 2 cosine x plus 3. Okay, so you have such an expression. What is a root? A root is a value of x, sometimes called a solution. It's a value of x that if you plug it on the left side, you plug it on the right side, they give you the same thing, right? That's a solution. We want to show that this equation only has one solution. Seems kind of hard actually, right? How are we going to show that it only has one solution? So what I would suggest to do is to bring everything to the other side and write it as 4x minus 2 cosine x minus 3 is equal to 0. And then define this function to be f of x. So we give a name to this function. 4x minus cosine x minus 3. Okay? Now, the basic idea is the following, or one important idea is the following. X is a solution of this equation is the same thing as saying that f of x is equal to 0. Do you agree? Okay? So now we're looking for x such that f of x is equal to 0. All right. We're going to break down the problem into two. The first part of the problem says that there exists a root of the equation. So we're going to find some solution of the equation. Just find any solution. What do you think we can do here? We're looking for a root of a function, for basically a point x such that f of x is equal to 0. What can we do? Yes?
Find the value of f(x) which is above 0 and below 0 and use the IVT to function across 0.
Okay, that's absolutely right. So the theorem we're going to invoke, you refer to it as IVT. What does IVT stand for? It's the intermediate value theorem. Or also known as IVT. So you point out that f of x is continuous. And suppose that we find, well actually let me draw the graph in a little moment to draw it better, but we need to find 2 points. One where the function is negative and another one where the function is positive. If you find 2 points, one where the function is negative, another one where the function is positive, there's got to be some point where the function has value 0. So for example, let's evaluate the function at 0. F of 0 is equal to 4 times 0 minus 2 times 1 minus 3 is equal to minus 5. Okay? Which is clearly negative. Okay? Now, let's try and find a point where the function has a positive value. This is 4x minus 2x plus 3. You play around a little bit with this and say that I evaluated at 2 pi. You know, I want to make it easy for me because this is cosine of x. The cosine of 2 pi is 1, right? So this is 4 times 2 pi minus 2 times 1 minus 3 is equal to 8 pi minus 5. 8 pi minus 5. I don't know exactly what that is, but I know it's positive, right? 8 pi, right? It's like 24 or more. Minus 5, gotta be positive. So positive. All right. So that means that now I can complete my graph here. This is 0. This is 2 pi. The function has a negative value at 0 and a positive value at 2 pi. And it's a continuous function. So if I draw this function all the way from here to here, there's got to be some point, I don't know where it is, but there's got to be some point somewhere in here, for example, where the function has value 0. This is when you say by the intermediate value theorem, there exists C in the interval from 0 to 2 pi such that f of x is equal to 0. Okay, that's the first part. And I wrote it in more words, but you can really only say by the intermediate value theorem, evaluate the function at 2 points, and then you say by IVT, that's it. You should probably mention the function is continuous, otherwise you might get a couple of points off. You see, if the function is not continuous, it doesn't need to be true at all. The function could jump from being negative to being positive without actually being 0 anywhere. Right? Okay, so that's the first part. The second part, okay, you need to look at the question carefully. Has exactly one root. How is that different from showing that there exists a root? What's the difference between there exists a root and it has exactly one root? What is that?
Because there could be multiple roots.
That's exactly right. There could be multiple roots. So we need to rule out the possibility that there's more than one root. Okay? So the second statement is there is no more than one root. Okay, how are we going to show this? Well, there's different ways to do this, but I think the easiest one is the following. You calculate the derivative of the function, and f prime of x is 4 plus 2 sine x. Remember that the derivative of cosine is minus sine. With this minus, the two minus signs cancel out, and the derivative of 3 is 0, so that's it. Now what can I say about this derivative? What is it? The derivative is always positive. How do you know?
No matter what value of x you put, it's going to be from 2 to 6.
From 2 to 6, that's right. Remember, the sign is not necessarily a positive number. The sign of x could be negative. But even if it's negative, it's not going to be less than minus 1. So this thing at most subtracts 2. This is bigger or equal than 2. So again, sign could be negative, but it cannot make the function overall negative. So this is bigger than 0. What does that mean for the function? If the function has the derivative bigger than 0, what does that say about the function? It's always increasing. And what does that have to do with the roots? Well, if it becomes 0 at some point, and then it starts increasing, and it can never go back down because it's always increasing, can it possibly have more than one root? No, right? It already goes through the x-axis once. It cannot go back. Okay? So the fact that the function is always increasing means that at most it can cross it. It can cross the x-axis at most at what point? Okay? That's it. So you put the two things together, there exists a root and there's no more than one root, and the problem is solved. There exists a unique root. Okay. Let me mention another problem. Oh, by the way, maybe I should say another way to solve this part 2 is invoking the mean value theorem. Okay? Mean value theorem, in this case, would be called the Rolle's theorem. Do you guys remember what the mean value theorem says, or Rolle's theorem? You should remember what these different theorems say, and you should probably also know them by name, because in the practice finals, there's some questions about just remembering what the theorem is called. In this case, Rolle's theorem is actually a very simple statement. Suppose that f of a is equal to f of b, and the function is differentiable. Then there exists some point where the derivative is 0. Okay? Let me say this again. The graph is very simple. The function starts here and ends here at the same height. So at some point, the function has derivative equal to 0. You see that? Yes? Okay? It's a special case of the mean value theorem. Okay. Suppose that this function f of x had two roots. So imagine this graph where you start at 0, go up, and then go back to 0. So at some point, the derivative must be 0, right? But why is that a problem? Because we just showed that the derivative is positive, right? So you cannot have a point where the derivative is 0. That's a different type of argument. You can also argue that way. I think it's more complicated and you don't need to really do that. So this is fine. But just be aware of this other way to do it. Because if you were asked, show that a function has at most 2 roots, right? Then you could invoke Rolle's theorem, but this argument here doesn't really work. Yeah, I'm not going to go into details, but anyway, be aware of this other way to do it. Okay? All right, so good. Let's talk about the chain rule. Derivative of sine of square root of x squared plus e to the 2x. Okay. So in class we talked about the chain rule a lot. One thing we didn't do, or at least we didn't do a lot, was to derivate compositions of more than 2 functions. In this case we have the composition of several different functions. The square root, the sine function, the function x squared plus e to the 2x. E to the 2x, by the way, is also a composition, right? 2x and e to the x. So how do we do the derivative of a more complicated function like this? Well, the trick is to think about this again as an onion. And you might remember that we described the chain rule as peeling an onion. So you start with the outside. This is the outer part. The outer part of this function. And this is the inner part of the function. So the function inside, everything that's inside the square root is the inner, and the function outside is the sine function. The derivative using the chain rule by definition is the derivative of the outer evaluated at the inner multiplied by the derivative of the inner. Okay? So this is the cosine of the inner multiplied by the derivative of the inner. Okay, so this way, even if the function is very complicated, by using this notation, you can always break it down into easier and easier parts. So now we already wrote this down. By the way, this is the cosine of this. This multiplication does not apply to, this thing is not inside the cosine, right? This is by itself. Cosine of this whole thing multiplied by this derivative. Now we have an easier function, and we can just continue to do it. So this is the cosine of square root of x squared plus e to the 2x multiplied by, and the derivative of this is, the derivative of square root of something is 1 over 2 square root of something, x squared plus e to the 2x multiplied by the derivative of x squared plus e to the 2x, right? Okay, what's the derivative of x squared plus e to the 2x? This is 2x plus the derivative of e to the 2x. Once again, it's a chain rule problem, really, right? The derivative of e to the 2x is e to the 2x times 2. So there you go. So the trick is to break it down into easier and easier parts. If you want it to be more and more precise, you can write this last part as the derivative of x squared plus e to the 2x. And then write a third line where you write down the derivative of that function. Question, can we cancel out these two things? I mean, these two square roots look very, very similar, right? Can I cancel out there? Why not? Right there. Square root times 1 over 2 square root. Okay, that's right. It's cosine of this whole thing. So you need to resist the temptation. even though it may be very tempting, to cancel out these two things. Okay, great. We can cancel out a little bit though. We can cancel out the 2. This 2 and this 2 here, we can cancel out with this 2 over here. And then write this down a little bit more compactly, but okay, fine. Let's write it a little bit more compactly and we finish. This is cosine of square root of x squared plus e to the 2x divided by square root of x squared plus e to the 2x. The whole thing multiplied by x plus e to the 2x. And that would be the answer. Hold on a second. Okay. All right, and I would also like to talk about a couple of problems that involve taking logarithms as a trick. So logarithm tricks, I mean, I call it tricks, is basically the question doesn't have anything to do with logarithms, but you take the logarithm to be able to solve the problem. For example, suppose you want to take the derivative of so this is a problem. Suppose you want to take the derivative of x to the sine x. Okay, so then what I would suggest is you consider the function y of x equals x to the sine x. You give it a name, y of x, and then you take the logarithm on both sides. What's this called again? What's the name of this technique? Logarithmic differentiation, that's right. Logarithmic differentiation can be used to simplify the derivative of certain functions, and this is no exception. So before you take the derivative of y, take the logarithm on both sides. So the logarithm of y of x is equal to the logarithm of x to the sine x. You can bring the sine x down, and this is sine x times the logarithm of x. Okay, so now we can derivate on both sides. The derivative on the left hand side is actually the tricky one. The right on the right hand side is a product rule, no problem. The left hand side is something that we call implicit differentiation. You don't really know what the function y of x is, but you're still taking the derivative. Okay, suppose that this was the logarithm of x squared. Okay, if this was the logarithm of x squared, how would you do it? It's 1 over x squared multiplied by 2x, right? Okay, so it's the same thing. 1 over whatever is in here, y of x, multiplied by the derivative of what's inside. What's inside is y of x, so the derivative is y prime. That's the reason why we need to multiply by y prime of x. Again, if think of y of x being equal to x squared, then you would perfectly know how to do it. When you have a general function like y of x, it can get a little bit tricky to think about it, but it's the exact same thing. It's 1 over y multiplied by the derivative. Okay, and on the right hand side we have a product rule. So product rule, the derivative of this is sine x times 1 over x plus cosine of x times ln x. And now what? Okay, Not exactly. Somebody just suggested that sine of x over x is 1. Actually, it's the limit when x goes to 0 of this thing that is equal to 1. I would suggest not to cancel and write that this is equal to 1. I saw some people doing this in the midterm, so it's good that you pointed this out. So this is not 1. This is still sine of x over x. Okay? Okay, but what we can do is we can multiply by y, exactly. So y prime of x is equal to x to the sine of x multiplied by sine of x over x plus cosine x logarithm of x. And that's that. Oh, questions? Okay, great. So notice that this is logarithm as a trick. Okay. Yeah, I don't know how to say this, but I think a number of you guys are tempted to write things like, let's say, y of x is equal to x squared plus sine of x, and then you write is equal to 2x plus cosine of x. What do you think is there a problem with writing this? This is a different problem. This is not the logarithm problem anymore. What's wrong with that? Yes?
You're saying y of x equals the second of both y's.
That's right. That's absolutely right. So please be aware of this. It's a very common problem in this Math 2A course. When you write something like that, what that's telling to me as a grader is that you think that the two expressions are actually equal to each other. You're saying that x squared is equal to 2x, and that sine of x is equal to cosine of x. Are they really equal? No. No, they're not equal. So this is wrong. Okay? And usually we don't care because we know what you mean, but sometimes we actually don't know what you mean. Sometimes it's more complicated, right? And you might get points off for this. So how should you write it then? It's easy. Just write y prime of x equal to that. That's it. Okay? Yes?
Put a bracket around the equation and put an apostrophe next to it?
If you put a parenthesis and put an apostrophe, then it's correct. But you need to do it right. So, if you're still talking about this function, right, then y of x is not the same as with the apostrophe, right? You would have to write, basically what you could write is you could write the first line, and then the second line is the whole thing with the apostrophe, right? And then you write this. So you still need to be careful. Basically, you can definitely use that notation of parentheses with apostrophe, but it wouldn't work to just write it like this in this case. You see what I'm saying? Okay. All right. So just be aware. This is not the same as this. You need to write y prime. Okay. Otherwise, we don't know what you're talking about. All right. So back to logarithm as trick. One more problem. Suppose that we want to calculate the limit when x goes to infinity of x to the 1 over x. This is a problem that was suggested to me by somebody in office hours today, on Wednesday. And it's an interesting problem. There's an exponential in here. When x goes to infinity, this thing goes to infinity, and the top part goes to 0. And infinity to the 0 is an indeterminate problem. In other words, just by inspection, you don't know what the answer is. If you had something like infinity to the infinity, this is not an indeterminate form. What is that equal to? That's infinity. That's right. So if you have something that goes to infinity to the something that becomes very, very big too, then the whole thing becomes very, very big. That's no problem. But in this case, you don't know. Okay? So how do we compute the limit of this expression? Well, once again, we're going to use logarithm as a trick. And the idea is to write y of x equals x to the 1 over x, and then take the logarithm of y. Same thing as before. This is 1 over x times log of x. Okay. And of course, this is ln x over x. Okay, great. So the trick is to consider the auxiliary problem. So I'm trying to write this very clearly. We're going to solve the problem limit when x goes to infinity of the logarithm of y of x. I want to stress this is an auxiliary problem. It's not the same as what we want to do. What we want to do is the limit of y of x. And now we're doing the limit of log of y of x. Okay? Different problem, but it's going to help us solve the problem. This is the limit when x goes to infinity of logarithm of x over x. And how do we do that? Limit when x goes to infinity of ln x over x. Well, the top part goes to infinity, and the bottom part goes to infinity. So it's an infinity over infinity problem. What does that tell you? L'Hopital's rule, that's right. So, by L'Hopital's rule, you don't have to write this, but this is what we're doing is, it's equal to the limit when x goes to infinity of 1 over x divided by 1. So I'm derivating up and down. Before I use L'Hopital's rule, I'm first thinking, can I apply L'Hopital's rule? I can only apply L'Hopital's rule when I have an indeterminate form. Infinity over infinity, 0 over 0. In this case, it's an indeterminate form, so we can apply L'Hopital's rule. And this is what? This is 0. The top part goes to 0. The bottom part's always 1. So the whole thing goes to 0. Question, are we done? We're not done because that's an auxiliary problem. Okay? It's not the original problem. So the original problem is, so back to problem. The original problem is x to the 1 over x. This is the limit of y of x. Okay? Now here comes the trick. This is the critical part. So pay attention. We want to find the limit of y of x. Okay? This is the same as the limit of e to the logarithm of y of x. That's the trick. Okay? Y of x is the same thing as e to the logarithm of y. Because these two are inverse functions of each other. Now, I know that the top part, the logarithm part, becomes closer and closer to 0. I know it because we just did it. The logarithm of y becomes closer and closer to 0 as x becomes larger and larger. Okay? So, if the top part goes to 0, that means that e to the that converges to 1. That's right, exactly. This is equal to e to the 0, which is 1. Yes, sir?
But wouldn't, in the very beginning, wouldn't infinity, so any number in the
infinity to the 0 be 1? Okay, that's a good point. All these calculations with infinities and zeros are kind of a back of the envelope calculation for something slightly different. It's not that we're taking a number and we're taking it to the 0 power. It's we're taking a number and we're taking it to the power of something that becomes smaller and smaller, right? So it's not exactly to the 0. It's to the something that becomes smaller and smaller. And if you take a really, really big number and you take it to the power of something very, very tiny, you don't really know what the answer is. It could be 0, it could be really big, whatever. It depends on the relative sizes of these numbers. Okay? That's a good question. Any other questions? Okay, so we have about 2 minutes left. So I think that should be it then.